Hello, welcome to this lecture video. So this is a continuation of our discussion on mathematical proof. So I am teacher Nelai, and this is the outline of what we discussed in this video. So our target is to discuss the last method, which is the mathematical induction. So let us first have some informations about the principle of mathematical induction. So we use this rather for a form with statements like for all n elements of n, p of n. And of course, we can show that it is true by giving example, but no matter how many examples we give, we cannot prove that the list, or we cannot prove that it is true with just presenting the list of examples. So how to do that? So to do that, we can prove using mathematical induction. And what is the principle of mathematical induction all about? So if P is a subset of N, such that, so for number one, we have one elements of P, and for every K elements of N, if K is element of P, then K plus 1 is element of P, then P is equal to N. So this simply means that you just need to show that it is true when N is equal to 1, when N is equal to K, and if we extend it until when N is equal to K plus 1. Thus, the procedure for a proof by mathematical induction is shown in this slide. So to prove for all n elements of n, P of n, so the basic step is to prove first that it is true for P sub 1, and to use inductive step like to prove that for each k element of n, if P of k is true, then P of k plus 1 is true. Thus, that's the time we can conclude that P of n is true for all n elements of n. So in answering this, we will consider this example. So we have a proposition that for each natural number n, 1 square plus 2 square plus until n square, and this is equal to n times n plus 1 times 2n plus 1 over 6. So let us answer this. So in answering this, let us consider step number 1, show that P of 1 is true. So we know that the given is 1 square plus 2 square until plus n square is equal to n plus 1, 2n plus 1 over 6. Okay, so just substitute 1 in place of n. So 1 plus 1 multiplied by 2 times 1 plus 1 over 6. And you will get, of course, 1 plus 1 is 2 multiplied by 2 plus 1 is 3. So 2 times 3 over 6. So this is 6 over 6, which is equal to 1. So since 1 is equal to 1, and the 1 is, of course, the same with 1 squared, which is our first term. Therefore, P of 1 is true. Number 2. Let us also show that it is true for P sub k. So to show this, we will just substitute k in place of our n. So similarly, this is just equal to k plus 1, 2k plus 1 over 6. So therefore, so of course, they have the same form because we just replace it with another variable. So since we obtained this value, which is of the same form with n multiplied by n plus 1 multiplied by 2n plus 1 over 6, therefore, P of k is true. So let us move to step number 3. So for step number 3, we are also going to show that it is true for P sub k plus 1. So to show that if P sub k plus 1 is true, so first we will substitute k plus 1 in place of n. So that is k plus 1, k plus 1 plus 1, and 2 multiplied by k plus 1 plus 1 over 6. So we just replace it with k plus 1. So simplify further. This is k plus 1, k plus 2, and 2k plus 3 over 6. So take note of this, because the next thing that we have to do is to show that the result when we substitute p sub k plus 1 is the same when we extend our given by adding n plus 1 to both sides of our equation. Okay, so let us again consider step number 4. So we have 1 squared plus 2 squared. So if this is equal to k squared, and we will just add k plus 1 squared on this side. So similarly, that is also what we are going to do on the other side. So we have k plus 1, 2k plus 1 over 6 plus k plus 1 squared. So we will simplify this. So we have k plus 1, 2k plus 1 over 6 plus 6k plus 1 squared. And then we will factor out. So if you notice, we have k plus 1 here and k plus 1 here. So we have 2k plus 1. So by factoring this out, so we have k plus 1. So what is left inside is k multiplied by 2k plus 1 plus 6. And we have still one more k plus 1 left over 6. So simplify further. This is k plus 1, 2k plus 2k plus, so we have 2k plus k and 2k squared rather plus k plus 6k plus 6. So we can now remove the parentheses. Over 6. So combined like term, that is k plus 6k is 7k. So what is left is k plus 1, 2k squared plus 7k plus 6 over 6. And if we will go back to the value obtained when we get p sub k plus, when we substitute rather k plus 1 in place of n in our equation. So this is equal to k plus 1, k plus 2, 2k plus 3 over 6. So if you will factor out 2k squared plus 7k plus 6, that is k plus 2 multiplied by 2k plus 3. So since p sub k plus 1 is the same with the value that we obtained here, therefore, the proof is complete. So this is how we use mathematical induction in proving. Thank you for watching.